we study the problem of computing representative one-cycles for persistent first homology group with Z2 coefficients. As we know, persistent cycles are born from a creator simplex and become trivial when the corresponding paired destructor simplex is brought in. Specifically, as interval module decomposition reveals the structure of persistence modules, we define persistent cycles which fit into this structure directly. Computing a minimal persistent one-cycle given a bar in the barcode of the persistent first homology is an NP-hard problem as we show in the paper. Instead, we propose a polynomial time algorithm to compute persistent one-cycles. The only time the cycles are not minimal is when there are more than one component in the cycle. These one-cycles are built using a shortest path algorithm. Hence, even though the cycles are not theoretically optimal, they are geometry-aware, making them tight. Also, our polynomial time algorithm is not less stable than an optimal algorithm, though it is much more efficient in terms of the time complexity. Given a simplicial complex K, and a filtration K0 through Km, if a simplex is positive, we find a one-cycle containing the simplex. This can be computed by Dijkstra's algorithm applied to the one skeleton of Ki-1. If the simplex is negative, we find a set of one-cycle whose annotation sum is 0. These one-cycles are the meaningful representative cycles in our software. Our software, based on this algorithm, generates tight persistent one-cycles on 3D, point clouds and 2D images. Let us see how the software works in various contexts in geometric modeling, computer vision, and material science.
First, we show our result on 3D point cloud and CAD models. On clicking on any barcode, we get the corresponding representative one cycle in the model. Notice how tight the generated cycles are. This is a genus 4 surface with H1 rank 8.
We can also see the cycles on the simplicial complex Ki, where I is the step the cycle was born in the filtration. Next, we investigate into persistent cycles found in images.
As is evident, we obtain quality segmentation using our software.
In this application, we identify the hemorrhage-affected region in the retina. Finally, we try to find meaningful cycles in crystalline solid as silicate glass. As seen, SiO2 has hexagonal cycles containing alternating atoms of silicon and oxygen.
We can detect these cycles perfectly for any size of the crystal structure. As demonstrated, PersLoop works seamlessly for